Hello, today it's my pleasure to talk about Brook Taylor. So first I'm going to talk about Taylor's series, which everyone knows about. Then I'm going to talk about the lesser known Taylor's theorem. Then we're going to use Taylor's theorem and we're going to show some code. So Taylor's series, this is something that you know from Calculus 2, and it's when you have this analytic function that's infinitely differentiable, and we will differentiate it starting with the zeroth derivative, which is the function itself, and then we're going to differentiate it 1, 2, 3 onwards for an infinite a number of times. And each time that we're differentiating it, we're going to be evaluating that derivative at some reference point x sub I, reference or home point x sub I, okay? And we're going to let that be the actual function. It will be in the infinite series. It will give you the whole function f of x evaluated at any x relative to that reference. So to get to that any x, you take x minus x sub I that goes with the first derivative. You take x minus x sub I squared goes with the second derivative. X minus x sub I cubed goes with the third derivative, and so on. And every time you take a derivative, you're actually dividing that derivative by 1 factorial for the first derivative, 2 factorial for the second derivative, 3 factorial for the third derivative, and so on. I could have taken the original function because sometimes we call that the zeroth derivative. So I could have shown that divided by 0 factorial being 1. So anyway, so that is in essence the Taylor series. It is a power series that's referenced to some x sub I, if you will. A lot of times we'll see discrete steps shown as x minus x sub I, or x sub I plus 1 minus x sub I. So when we do this, we have this h that's going forward. It's like a forward-looking h, and we'll show that h replacing the x minus x sub I. So sometimes we'll show that. So to get that equality, to get the actual equality, this is an infinite series. Not super useful if you want to be like Nat's ass accurate. I think it's useful to talk about truncation. So this is when you take Taylor series and you stop after the first derivative, and you call that first order. You stop after the second derivative, you call that second order. You stop after the third derivative, you call that third order. And this could give you an approximation that is near what the function would be. However, if you want to get a little bit better, let's bring in Taylor's theorem. So here we need to think about the function that is at least n plus 1 times differentiable. And we can do the same thing that we did earlier. We take derivatives, 0, first, second, third, up to nth. And then we add in this r sub n term called a remainder term. And that remainder term is evaluated at the n plus 1th derivative of f, and it's evaluated at this c. C is some value between x sub I and x. Okay, I don't know what it is. I don't know what this value is, and it turns out it doesn't matter. Okay, it turns out that I've never had to solve for what c is, but it's not x. It's not x sub I. And you're going to multiply it, and you divide by n plus 1 factorial, just as any other term. You're dividing by whatever the derivative is. You're dividing by that factorial. That's fine. But it is x minus x sub I to the n plus 1th power. Okay, so we have that. But it just amazed me that this is a true equality. That, yeah, there's going to be some c value in there. I said there is no way this is completely true, the equality aspect, okay? But it turns out that it is, and sometimes you'll see this error term, this remainder term, r sub n, it can be thought of as this error term, and you'll see it written as with what they call the big O notation, as big O in terms of h to the n plus 1 power, because that's the power of h that is prevailing here. Okay, so that's Taylor's theorem. It's amazing. At first blush, I did not believe it, but it relies on this Kc value that I was speaking of earlier, this Greek letter. I think it's a Greek X, but it's pronounced Kc. And anyway, so it is an equality, and we never really have to solve for this Kc value, because the idea is that we want this remainder term to be very, very small, very, very small, okay? And it's being small for a number of reasons. H is typically small itself, and each time that you take h to another power, so h is small itself, h squared is going to be much smaller, h cubed much smaller, hn very, very, very small, and then you've got h to the n plus 1, so that's going to be minute. And then you're dividing by progressively a bigger denominator. So, 2 factorial, obviously 2, then you got 6. If it were 4, that would be 24. Each time, each derivative that you take, you're dividing by an n plus 1 factorial, and ends up being a very large number in the denominator. So the idea is that remainder just gets smaller every term that you come on. Let's take a look at a really good example in the book where the function that they're relying on is cosine. The home position is pi over 4, so our x of I is pi over 4. Our h is pi over 12. So when we're trying to evaluate the next point, it's going to be pi over 4 plus pi over 12, which is pi over 3. And pi over 3, we know that's going to be 0.5. The cosine of pi over 3 is 0.5. So let's look at some different terms, how they kind of combine. So if we were to evaluate it, say the 0th order, in other words, just the function, we're going to get cosine of pi over 4, and that's going to be 0.707. And if we think about relative error, we're going to look at 0.5 minus that 0.707 divided by 0.5, absolute value. The book likes to show percentage. I'm not a big fan of that. I don't show percentage, but we can accept it. I think it's pretty straightforward. So 41.4% is what they show for the 0th order. Okay, then they go ahead and add a term. So they progressively add terms, which is quite frankly what I do. So progressively add a term. Now the first derivative of cosine is minus sine. So when we put in the minus sign of our home position, pi over 4 times h being pi over 12, we put that together, we get 0.521, etc. And that's actually going to give us an error of 4.4% at first order. So this 0.4 is incorrect. That's a typo there. So that's first order. Second order approximation, we're going to add in the second derivative term. And the second derivative is minus cosine. So we bring in the minus cosine, and now you're starting to see where you're dividing by that 2 factorial. And so we're dividing by 2 factorial, or just 2. We're going to multiply by h squared, which is pi over 12 squared, and we're getting 0.497 and change. And that is correct at 0.449%. So the second order, and it's showing the derivatives as they progress, and it's showing how as you add more terms that you are getting closer and closer to that 0.5 that we should be getting. We actually shoot past it a little bit here, but this error is actually smaller in the 6th order than the 5th order error. Okay, so let's take a look at how we can program this up and sort of doing it in somewhat of a generic way. So what I do is I've created this Taylor function. So this is in my day 5 subfolder. So I call it Taylor f, and f is a function. So we're actually going to send a function to my function. So they call this a function handle. and it's going to come in as a function. I'm actually going to call it in my for loop here in just a moment. I'll explain that in a moment. So I'm bringing in the function. I'm bringing in the n. That's the order that I want that Taylor function to be evaluated to. It could be 0 all the way up to 6, as we just were witnessing. My x sub I, that's my reference or my nearby point. That's my home point. That's where I'm referencing as pi over 4, what we just talked about. H is going to be my step. So it's going to be like for pi over 12 in the example that we're kind of looking at. Okay, so those things come into my function. And what I do, the bulk of the function is contained in this for loop. And I actually start the for loop at 0. So my k is going to increment up to and including n, which is the order I want this thing to end at. N could be 0. It starts off as 0 just a minute ago, and it could be, all the way up to 6 from what I was talking about earlier. So it's going to be this for loop is going to run at least once, and it's going to run all the way to n. So each time it's going to take our previous xi. So xi1 is a local variable. It's a local variable that I'm going to actually return, but I'm going to initialize that local variable as 0, and then I'm going to progressively add to it, okay? So first time through, when k is 0, I'm going to be evaluating the function with the 0 derivative, and I'm going to divide by the 0 factorial, which is 1, and I'm going to multiply by h to the 0, which is 1. So the first time through the for loop, it's going to be just evaluating the function. The 0th derivative, the function is all that's going to be done because that's 1 and that's 1. So that's the 0th. And then if I am going to go and do the first derivative, or if n is 1 or greater, then what I'm going to do is take the previous term, which I've just calculated, and I'm going to add to it the function evaluated for first derivative when k is 1 for my current home position or reference position. I'm going to divide by factorial 1, which is 1, and I'm going to multiply by h to the 1. So that's it. And then I just accumulate that x sub I, and then if k is 2 or higher, then I would be evaluating, k would be 2, so it's going to go to my function, and I'm going to be asking for the second derivative of my function evaluated at the reference position or the home position, divided by factorial k times h to the factorial 2, if k is 2 now, times h squared, and I just keep doing this until I get to n, and then I return from that function. So I can do any function this way. I just have to hard code this function, this f. So that's what I'm going to do. And what I was showing you is I was progressively going through the Taylor series expansion all the way, and hopefully up until at least n. So hopefully we don't have to worry about the remainder term here. Okay, so here's my cos function, and you could see that this works like you bring in the home or reference position x sub I, and you are giving it a second input. That's the derivative that you're looking for. Let's say my derivative I'm looking for is 0. Well, it's going to switch on 0, and it's going to return the cosine of x sub I. All right, so that's one thing. If k is 1, it's going to be looking for the first derivative, and the first derivative, as you know, is minus sine of x sub I. If you want the second derivative, well, that goes to minus cosine of x sub I. If you want the third derivative, that's going to be sine of x sub I. So you can see how this progression, and you can check me out that the fifth derivative of cosine is indeed minus sine of x sub I. Okay, so this is how it progresses. And here's my script that generated the same table that was in the book. All right, let's walk through it. So now I'm going to call my Taylor function, And how I call my Taylor function, I give it an at cos func. So when I say at, that at symbol in MATLAB means to send the function handle so that inside the Taylor function it can use cos func. Right? So that's what this at symbol means. Very, very powerful. It's called a function handle. And I'm going to be sending it I. So I'm going from the I equals 0 order and through my loop. And I'm going to be going all the way to 6, I equals 0 to I6. So every time in the loop, I'm going to be adding another order and printing out what the results are. Okay? And then every time through, I don't have to do this, but every time through, I go ahead and calculate what the true value is. And then I show my error in terms of, not a percent, but just a relative error. And then this fprintf, and very, very powerful. Fprintf is a very powerful function. And anytime you see a percent, the percent in this character string, you see a percent. That percent corresponds to a certain variable that is coming after the character string. Okay, so for example, if my current through the loop, if my current I is 0, that means I'm evaluating it to the 0th order first time through. So that D means decimal, and it's an integer, so it's going to print that as a decimal integer. This next one is x sub I, so that's my value I'm getting back from the Taylor function, and that's going to be printed with 15 decimals to the right of the decimal point. That's what this means. The F means double, and that dot 15 means I want 15 decimals to the right. And then it's going to print my error, same thing, 15 decimals to the right. And then for some reason I said, I think I'm going to show my true value too every time through, 15 decimals to the right. So you see the 15 decimals to the right for my value. You see my 15 decimals to the right for my error, 15 decimals to the right for my true value. And let's see how it compares with the book. So the book, and this shows the sequencing of the derivatives, right, that we had over here. Here's my values that agree very nicely with what's up here. And here the percent. Now remember, these are percents. I don't like doing that, but they do agree with the values up here. Off by, these are differ by 2 decimal points, obviously, since these are percents. So then I took and did a script 1. In my script 1, what I did is I marched, changing my h. I marched from where it would be minus pi over 4, so that would be 0, and I marched all the way to pi over 2 and created these graphs. The true is magenta, and this is in my day 5 code, so you can go check out, see how this looks. So the true is magenta. Okay, the first order is just going to be a line. Well, that's what it is. It's just first order, so that slope is not going to change. Second order is green, so that's going to be like a quadratic or a parabola. And the third order is going to be a third order curve. And progressively, as I go higher order, it starts to trend towards that magenta. So I encourage you to look at my day 5 script 1, my day 5 folder, and look at my script 1. Okay, so we've taken a look at Taylor series today. We've looked at the Taylor theorem. We used it. We looked at some different code for it. So hopefully you've enjoyed that.